Good evening, everyone. This is Ranamay Saha. I'm a PMRF scholar in the Department of Mechanical Engineering at IIT Kanpur, and today we will be uh, taking up our 10th problem-solving session from Manufacturing Process Technology 1 and 2 of the current running NPTEL course. Uh, Today we will actually be discussing the assignment questions from our last week. That's assignment 9, solutions, and discussing up any doubts you might be having, discussing and clarifying your doubts regarding the assignment questions from last week. And then we will move up and see some of the problems and solve some of the problems out of current fixed content, okay, that is electro discharge machining process. Let's move ahead. Let's start our session. Firstly, we will be discussing assignment questions from last week. Let's start for USM process. The question was, what should be the nature of the tool used in case of ultrasonic machining process? So you know that for USM process, the tool must be made up of a material with high wear resistance, because the abrasive particles are always very hard. So the tool which is striking those particles must be tough enough so as to have sufficiently high wear resistance, high fatigue strength, and again have high ductile properties. So some commonly used materials are mild steel, stainless steel, brass, or other similar alloys which allow it to withstand the vibrations and minimize tool wear during machining. So option B, which says the tool must be ductile and tough for USM process, is the correct option here. Hope you all could have answered this question. The next question asked you for a hollow tool in case of USM. The thickness should be how much? So looking at the options, because the tool is hollow, so the wall thickness should be at least 0.5 to 0.8 millimeters to ensure sufficient rigidity and prevent tool vibration issues during the machining process. If the weld thickness is too thin, the tool can easily deform or vibrate excessively under the ultrasonic vibrations, leading to inconsistent machining results and potential tool failure. So option 1, that the tool, if in case the tool is hollow, so as to sustain the high frequency ultrasonic vibrations, the thickness of the well should be at least 0.5 to 0.8 millimeters. All right. So option A is correct here. Then in case of abrasive jet machining process, material removal is by focusing a stream of abrasive laden gas to impact and impinge on a surface, you know that, and converting kinetic energy into impact energy and eroding the material. So impingement of particles leading to material erosion is the process or principle of material removal in case of AGM process. So AGM is effective on hard and brittle surfaces, again, as soft resilient surfaces like rubber or plastic resist chipping and brittle fracture, and rather result in addition of the particles into the workpiece surface. So in this question, option C, which says in AGM process, material is removed by brittle fracture of workpiece due to impingement of fine abrasive particles only, is the correct option. The next question actually asked you to find out the meaning of those variables C, O, A, and B, which indicate different tool position during the USM process, ultrasonic machining process, right? So C, is the starting position of the tool, right? And then O is the mean position A is when the tool has touched the abrasive grain, and B actually indicates the bottom position when how much the tool has penetrated into the grain. Okay. So in ultrasonic machining, the material removal rate increases with an increase in feed force, but after a certain point, which is called as critical feed force, it decreases again. So we have seen such kind of variation of the MRR with different parameters during our last session in detail. So you know that after a certain point, the critical feed force, uh, although goes on increasing, the MRR will decrease, right? As the feed force increases, more abrasive particles are pressed against the workpiece, leading to a higher material removal. However, if the feed force becomes too high, right, the abrasive grains can get crushed under the heavy load. So that was what about we talked about crushing of grains, right, in our last session, reducing the effectiveness of the machining process and causing the MRR to decline. So option C here is the correct option, where C stands for top position, O stands for mean position, A stands for the grain touching point, and B stands for the bottom point, which is indicating that this much percentage of area the tool has actually penetrated into the grain. Then the next question was about the MRR relation with feed force, right? So just now we have discussed that due to crushing action, the MRO first increases with increase in feed force, but after that, after a certain critical feed force value, it starts decreasing. So option B is the correct again here. Now the next question is about the principle of MRO in case of material removal rate in case of your ultrasonic machining process according to the Maxwell's model, where you know that the material removal rate is directly proportional to the volume of material removed by impact V, okay, and then directly proportional to the number of particles making impact per cycle Z and the frequency nu. So option A becomes the correct option again. The next question asks you to actually identify the pictorial representations, right, of certain schematic diagram. So which of the following feed mechanisms 1 to 4 are used for the USM process? If you can see the first diagram, you can see a lever, okay, which is resting on a fulcrum. So here you have a counterweight with lever and fulcrum as being the feed mechanism in case of this kind of USM process. In the second case, again, you can see there are some solenoidal turns here, which are again connected finally to the uh, grain insertion over the tool or the workpiece. So here it is an electronic solenoid control. The next one is a belt and pulley mechanism. So it deals with a counterweight, which is connected to a rope through a pulleys. So option C is about the counterweight with rope and pulley. And finally, option D, which is again hydraulic or pneumatic controls. You have uh, pneumatic controls. You have one inlet, one outlet, and depending upon the amount of feed above, amount of feed pressure above or below, we can have an hydraulic or pneumatic control depending upon the fluid used. So option B is the correct option again. Next, the question asked about what abrasives can be used for both AUSM and AGM, ultrasonic machining process and abrasive jet machining process. So, you know, aluminum oxide and silicon carbide are the most common materials used as USM or AGM tools, depending upon their properties and the cost associated. So both aluminum oxide and silicon carbide ceramic materials that can be used as abrasives in AGM and USM process. They have good abrasion properties or different workpiece materials. So good abrasion properties as in ductility and toughness, right? So they have good resistance to wear, fatigue, right? So option A and B both are correct in this case. Then we had two simple numericals. The first one is say that the jet velocity for a volumetric flow rate of 628 centimeter cubes per second and 2.4 millimeters nozzle diameter. So it is a very simple question. The volumetric flow rate is given, or you can say the Q value is given as 628 centimeter cube per second, and the nozzle diameter is given, from which you can actually find out the area of discharge. If you can find out the area of discharge, you know the flow rate is actually directly related to the product of area of discharge multiplied by the velocity. Okay. So from that relation directly, if you plug in the values of Q average, that is the volumetric flow rate, and then the area which you can calculate easily for a circular nozzle area, it is pi r square, 0.12 being the nozzle radius. You can find out the velocity of discharge as Q average upon A, which is coming out to 138.82 meters per second. So option D becomes the correct option. I hope it was an easy task for you to solve this kind of question. The last question said for AGM process if the mixing ratio is 0.25. So we have discussed about mixing ratio in our last class. So this is a similar kind of question in which the mixing ratio is 0.25, and the density ratio of abrasive to carrier gas is given as 50, then the mass ratio was to be found out, right? So this is very simple. You can find out the mass ratio as the uh, ratio of the product of density and volume of abrasives to the cumulative density of abrasive and uh, volume of abrasive product plus density of gas, volume of gas products. Okay. So from that, mixing ratio is given as 0.25 and density ratio of abrasive to gas is given as 50. You can just plug in the values and rearrange and find out the option C, 0.926 is the correct answer. Okay. So these many were the questions asked in your assignment. I hope nobody have any doubt regarding these questions. If not, then I will give you some time. If not, we will proceed to discussing some of the problems out of your current week's content. Okay. Before we move to solving problems out of electrodischarge machining process, let us firstly look what is the mechanism of material removal in EDM process. So for a one-liner, you know that material removal in EDM process is actually happening by melting and evaporation. But if you look at the detailed process, so let us first look at the circuit, RC circuit. So there is a you have an supply voltage V naught. You have a resistor connected for the drop, and then you have a capacitor for storing the charges, and then you have a tool, okay, which is generally a cathode, which is a brass or copper made, and then you have a workpiece, which is connected to as the anode. Okay. Now, once you apply the supply voltage, one point is reached where which is called as the discharge voltage point, a particular point in the voltage where something happens. Okay, so with different time points, you can see there are uh, cyclic phenomenon where the discharge voltage is reached. Okay. So what happens is, so electron once the discharge voltage is reached, electrons accelerate towards the anode, right? From cathode, there is a tool, electron starts accelerating towards the anode, which is the workpiece. Then during the process, what happens is collision of the electrons with other molecules of the dielectric mediums. You know there is an insulating dielectric medium which is there um, as a solution, okay, to with which the electrons collide to break down them into electrons and ions. Yeah. So you have additional electrons and ions in the solution. Now the ions, on the other hand, goes on accelerating from the workpiece, which is the anode, towards the tool, okay, which is the cathode. So there is a continuous motion of electrons from the tool, that is cathode, to the workpiece, which is anode, and ions move from the workpiece to the tool. Okay. Now, as the electrons and other hit the other molecules of the dielectric medium to generate further more ions and electrons, there is a generation of ionized column of dielectric fluid molecules. Okay, so once the length of this ionized column is sufficient to actually connect the two electrodes, there is a connection between the two electrodes, that is the cathode and the anode, that happens. Once that happens, there is an avalanche of electron which generates a spark. What do you mean by avalanche of electron? Avalanche is this is a high energy bunch of electrons moving at very high speed. That is called an avalanche of electrons, and that generates a spark which has a temperature sometimes reaching from 8,000 to 12,000 degrees centigrade. This temperature then melts and vaporizes electrode materials evacuated by a mechanical blast, causing small craters at the electrodes, right? So you find small craters on both the electrode surface. However, the more number of craters is or more volume, more larger craters are formed in the workpiece. This is the anodic surface. We will come to the reason for that. Okay, so the next question is, why is this emerger more from an anode than a cathode? Okay, so there are three particular reasons. The main one is the momentum of the stream of electrons is more than that of the positive ions impinging on the cathode. The ions being heavier, right? The velocity is lesser than the electrons, and the momentum hence is again less. So momentum on the stream of electrons is more than that of the positive ions impinging the cathode, which results in more material removal from the anode surface. Secondly, there is something called pyrolysis, which is the process of thermal deposition of materials at elevated temperature, often at inert atmosphere. So during the EDM process also, this pyrolysis thing happens where a carbon layer is deposited over the cathodic surface, right? So being negative in nature. So pyrolysis of the dielectric fluid creates thin layer of carbon on cathode, right? Again, uh, a compressive force is developed on the electrode surface. Why? Because as the ions are heavier than the electrons, the ions create a compressive force on the cathode surface, which actually prevents the emitter substantially as compared to the emitter out of the anode surface. So these three reasons actually lead to more significant material removal from the anode surface as compared to the cathode surface. So I hope you have got this point. In that case, we'll move ahead and discuss one more important concept, which is called uh, what is the nature of an ideal dielectric fluid in EDM process. Okay, so first of all, why are dielectrics used? So dielectrics are used as a capacitor for storing energy, right? The dielectric material in a transformer is used as an insulator, okay, as well as a cooling agent. So similarly, in case of electrodischarge machining process, dielectrics act as an insulator or neutral nature, which is used for storing energy, which acts as a capacitor, right? So first thing is that the dielectrics should have chemical neutrality. Okay. Secondly, they should not have very high viscosity so that the flow of the charged species within the dielectric becomes difficult, right? So the dielectric material should have low viscosity. Again, toxic vapors should be absent because this can hamper or interfere with the melting and evaporation process and can actually influence the net emitter value and hence lead up to an inefficient electrodischarge machining process in terms of outputs. So inflaming tendencies, of course, shouldn't be there for safety reasons, and the low cost is the most common and important parameter whenever you are designing any manufacturing process. So these many are the most important parameters which are required for an ideal dielectric fluid in electrodischarge machining process. So having said that, can somebody tell me that why can't we use water as a dielectric? So water is also having low viscosity, toxic vapors are absent, sense of inflaming tendency, and it is of course a low cost material. So the question comes: is water neutral, charge neutral? No. So water has conductivity, and conductivity of water actually causes distortion of the workpiece because the electrodes are always under potential difference. One is connected to the positive potential, another is connected to the negative potential. So there is a potential difference, and conductivity of water can cause distortion of the workpiece. Secondly, water can lead to rusting on sustained contact with the electrode surface. So that way, the electrodes can be eroded, corroded, and we may not get an efficient EDM process. Okay, then the conductivity of water can cause distortion of workpiece, and that may indirectly cause wastage of power because mm, there is no capacity for there is reduced capacity for charge storage, and hence more power can be required for the same amount of emitter out of the material workpiece surface. So these are the reasons why you can't use water as an electric. So these many are some of the concepts which I wanted to discuss with you all. And once we have discussed that, we will move and see some of the problems out of this electrodischarge machining process. Okay. The first question is, it asks, we have discussed, right, that EDM process, MRS starts the formation of craters, small craters on the anodic surface, and uh, if you consider those craters are maybe of spherical shape, of course, these are not spherical always, and it not be spherical, but considering these are spherical in nature, can we find out the volume of the crater formed formed during EDM if the depth of the crater is given as HC. Okay, so give it a try. Here are some of the starting hints which I have provided for you all. So crater volume during discharge. So we can assume the crater formed is a part of a sphere of radius r. Okay, so the crater, this one you can see is the crater. It is embodied in a larger sphere which is having a radius r. And then you can use some Pythagoras concepts to find out the radius of this crater, which is a. Okay, and then you can find out what is that value. Okay, so point A and point B, and then you can simply integrate to find out the total volume of this entire crater formed. Let's give it a try, and then we will discuss the solution in details. Okay? Let us look at the solution, how to come out with the volume of the crater formed during EDM if the depth of the crater is given as hc, for instance. So, as we discussed earlier, if we consider the crater be somewhat circular or spherical in nature and being a part of a larger sphere in which it is embodied, the radius of the larger sphere be r and the radius of the crater be small a. Okay? So using Pythagoras, we can see from this particular triangle. So if this is r, then this dimension of this particular feature uh, is also must also be r, right? Being both being part of the of a bigger sphere into which the crater is embodied. So using Pythagoras, you can see r minus hc square. Okay, r minus hc is the height of the crater or depth of the crater, r minus hc square plus a square, which is the radius of the crater here, equal to r square. Okay, considering this right angle triangle. So just simplify that equation to see r square plus hc square minus twice of r hc plus a square equal to r square. For the simplifying, you can find out the value of r to be a square plus hc square upon twice hc. So now finding out the length at point A and point B. Okay, so this is point A, which is nothing but r minus, this is not rc, this is actually hc here, right? So r minus hc, okay, equal to a square minus hc square upon 2hc. And you can just replace this r as r minus hc, and then you can find out the length at this particular point, and then again at particular point b we have, so at this point b we have simply r, so r is nothing but a square plus h square upon twice of hc. Moving ahead, so this be the hemispherical crater which we are talking about with a thin differential dimension dy as the height, is the radius r, as we discussed earlier, is the radius of the sphere, bigger sphere into which the crater is embodied. So now we can find out the volume using this conventional method, which you all must be already acquainted with. So it is pi a squared dy, dy with the differential dimension thickness of this particular strip. Okay, and this once you integrate from a to b, so this is the same crater which we are looking out here. We have just inverted it for the ease of understanding to find out the integration. So from a to b, if you integrate it, it is a square minus hc square upon 2hc to a square plus hc square upon 2hc, right? And a square value on the variable a square you can find out using Pythagoras as r square. So if you consider, okay, this height as y, okay, if you consider this height as y, then you can find a square value as nothing but if this be y, then a square value is nothing but r square minus y square. Okay? If this dimension be y, so pi r square minus y square d phi, integrating it from point A to B can actually get you the total height, or the total volume, okay, of this uh, crater in terms of the height hc. Okay, so here it is follows, then becomes pi r square of y from a square minus h square upon 2hc to a square plus h square upon 2y hc minus pi by 3 of y cube a square minus h square upon twice h to a square plus h square upon twice h. So these are the limits of integration, and also integrate it as r square minus y square dy. So the first variable, the first term, it becomes dy integration, it is y. So you have here r square y. And in the next case, you have the integration of y square dy. So that is y cubed by 3. We have taken out the 1 by 3 out of bracket and integrated y cube from between the lower limit to the upper limit. Okay, so the volume of crater then becomes pi by a6 h3 in bracket 3a square is the radius of the crater and h is the depth of the crater. So we have a generalized time h and just comparing it to z, so it is proportional to z, which gives the indication of volume removal by each spark. Okay. If you look at it empirically, it has been found that the HC, the height of the crater, actually varies with a constant K1, which is nothing but uh, as a constant, which is having various values for different kind of materials, and then you have this W, which is the spark, which indicates the spark energy in case in terms of joules. Okay, raised to the power 1/3. And then A, which is the radius of the crater, again varies as half of K2, which is again constant, and then W raised to the power, W is the spark energy in joule raised to the power 1/3. Okay. The dimensions being centimeters. So you can rephrase the volume of crater removed as pi by 6 K. Take out K as a constant outside, and then you have 3/4 of K2 square plus K1 square multiplied as W, right, which is the spark energy in joules, centimeter cube. So this is how you arrive at the volume of crater which is removed and can relate it to the spark energy W. Okay. Uh, Having said that, you can see the various values which I have shown just as a representation of what values can these constants K1 and K2 take. Okay, for copper, K1 is 0.4 and K2 happens to be 0.045. These are all empirical relations. Having said that, let's move to a numerical question for resistance capacitance relaxation circuit. Okay, it says in RC type generator, the maximum charging voltage is 80 volt. Okay, and charging capacitor is 100 microfarads. You have to determine the spark energy. So the charging voltage is given to be 18 volts and capacitance is given to be 100 microfarads. So using the simple direct relations which you have derived in your regular classes, it is half charging or discharging voltage square, okay, into capacitance in bracket 1 minus e to the 1 minus twice of discharging or discharging time upon C or M. Okay, so here TD is 0. Okay, so this term goes off and you are left with the total energy being related to half of C VC square, okay, or VD square in some case. You can replace that. It's a similar thing. Okay, so it becomes E is equal to half of the capacitance is given to 100 microfarads. Okay, and the voltage, charging voltage is given to be 80 volts. So just finding out the product, you can find out the total spark energy required being 0.32 joules. All right, so just take a note and then we'll move ahead to discussing our next problem. So next problem asks for a RC type generator to get maximum power dissipation during charging. So we have seen while deriving the EDM process, we have seen that the charging voltage is actually 72% of the supply voltage V naught. So it is 0.716. We now determine the ideal time for the RC value as 10 ohms and capacitance value as 200 microfarads. Okay. So just using that standard equation, you can take the logarithmic from both LHS and RHS. You can see a log of natural log of V naught minus VC upon V naught. V naught be the supply voltage, VC be the charging or discharging voltage equal to minus of VC, the charging time upon C multiplied by RC. Okay, just plug in the values. You can find out the TC, okay, the idle time as 25 17.56 microseconds, or you can say 2.517 milliseconds. Right? It's a simple and direct question. Just take a note and then we will move to our next question. So let's move ahead to our next question. It is again resistance capacitance relaxation circuit which is used for an electrical discharge machining process. The discharge voltage is 100 volt at a spark cycle time of 25 microseconds. The average power input required is 1 kilowatt. Okay, the capacitance in the circuit is what? You have to find out. This question came in your GATE 2015. It is a very direct question with a simple twist. So the discharge voltage is given as 100 volt. The charging time or idle time is given as 25 microseconds. Energy is given as 1 kilowatts. You have to find out the capacitance. So use the same standard formula. So here again, this terms goes zero because TD has tends to be zero ideally, and then you have to find out this value energy, okay, spark energy. So you have given the power input required is 1 kilowatts. So then you have to find out the energy. So what happens to the unit for power? Okay, it is joule per second, right? Now, and then cycle time is given as 25 microseconds. So what happens to be the unit of energy, spark energy, that is joules, right? So how do you get that? Just multiply the power input with the spark cycle time. So you can find the total energy as 1 kilowatt, that is 10 raised to the power 3 watts, multiplied as 25 microseconds, which happens to be the total energy becomes then this one, which equates to half of C of 100 squared. Then from that you can find that the capacitance to be around 5 microfarads. Okay, so that's how you get it. So take a note of this, and then we'll move to our Now the next question is about an electrodischarge dealing process, which is again similar to electrodischarge machining only. So here a 10 millimeter square hole has to be drilled in a low carbon steel plate of 5 millimeter thickness. Brass tool and kerosene, kerosene is a dielectric, is used here. The resistance and capacitance of the relaxation circuit are 550 ohms and 10 microfarads. The supply voltage is 200 volts and the gap is maintained such that the discharge takes place at 150 volts. You have to estimate the time required to complete the operation. Okay. So how do you find that? How do you find the time required? So when you if you know the M error, right? That is material removal per unit time. If you can find out the total volume of material removed somehow and uh, you can also find out the MRR value, then the ratio of both can actually give you the time, right? So you can find, if you can find out the rate of removal and the total removal, then you can find out the time required to complete that removal process, right? So first you can find out the amount of energy released per spark, which is half CVD square, as we have seen in earlier cases. Uh, you can simply plug in the values of capacitance and discharge voltage. You can find out the total energy is 0.113 joule. Again, the cycle time you can find out by this equation. You are already familiar with it. So that is R for resistance, C for capacitance, B naught for supply voltage, VD for discharge voltage. You can simply plug in the values and find out the cycle time is 7 into 10 raised to the power minus 4 seconds, okay, or 0.7 milliseconds. Say that you can find out the average power input, okay. The power input, as we discussed, can find out the power input as energy upon time. So that is 0.16 kilowatts. So now, since the workpiece is made up of steel, we can use the empirical relationship for determining material removal rate. So you know the empirical relationship for finding out MRR in case of steel workpiece. For EDM process, that is 27.4. A power input W raised to the power 1.54. Just plug in the values of work in power input in terms of kilowatts, that is 0.16, and then you can find out the total Q as 1.633 millimeter cube per minute. So the total volume of material to be removed, then you can, the dimension of is given, it's a 10 mm square hole. Okay, the thickness is 5. So the total volume is 10 square into 5, which is around 500 millimeter cube. So you have the total amount of uh, material removal, you have the rate of material removal. You can simply divide the total amount of removal by the rate. Then you can find out the time as 306 minutes. Okay. So this is how you approach this kind of problems. Just take a note, and then we'll move to our last topic for today's discussion. So our last topic today is about the role of cavitation in case of EDM process. So what is cavitation? Now, You know about jet engines, right? You know about jet engines, you know about high-speed rotating propellers, where the speed is so high that the pressure often drops below atmospheric pressure, right? And even boiling starts at very low temperatures. So in that case, some bubbles are formed, and when this bubble bursts, they simply erodes the material in which they are contained, the surface of the containers. So in case of electrodischarge machining process also, you can see that if you are simply plotting the curve for pressure versus time, so where the pressure is going below the atmospheric level, you can see that the MRR during particular spark cycle Q is actually going to be the maximum, right? So in this region where the pressure is actually falling down the atmospheric pressure, and you can see the MRR is getting to the maximum. Why? Because of this cavitation process, which actually adds to the material removal rate through uh, conventional impinging action of particles. So sorry, through melting and evaporation process in case of helium. So that conventional MRR material removal process is actually augmented by material removal due to the cavitation process. So that's why in the low pressure regions where pressure falls below the atmospheric pressure, you have the maximum peak of MRR being achieved in case of helium process. That's where I conclude today's session. If you have any doubts, you can please ask me. Okay, thank you.